Right, so give a round of applause to Scott, and we'll get going in the second talk.
Hello, thank you very much. This talk entitled 4,000 Containers for Engineers, it's not supposed to be impressive at all. I mean, it's more about the journey that we took to get to this stage. I mean, we're a very, very small company. The team is actually now 5, so apologies for that. When I offered the talk, there was only 4, but we transferred someone from a different team, which is quite nice. So it's about our journey and more around operational stuff more than just deploying containers. Right, deploying containers is easy, but how do you keep them up? How do you monitor them? How do you know things are working? So I am Scott Perham. I used to work at Microsoft before I was at Polystream. I worked for a game company called Lionhead, who some of you may know. The project I was working on got canned, and in typical Microsoft fashion, the entire company got shut down and everyone got sent on their way. About the same time, a couple of people, Bruce Grove, who's the CEO of Polystream, and Anna Billiard, who's the CTO, came together in Guildford. They'd been working on something for quite a while, and they decided now was the time to really push it. And it just happened to coincide with the tearing down of Lionhead. So he managed to grab a few people from there, and we started Polystream. So Polystream is a cloud gaming service, essentially game streaming. Obviously streaming is not a new thing. Streaming's been around for a long time. Interactive streaming is the obvious next step, right, from CDs and video and things like that. But there's a problem. Everyone's trying to do it in the same traditional way that they do video streaming, which is just take a GPU in the cloud, you just run something through it, and then you take the output. The problem is it doesn't really work because it's not scalable, right? There's not very many GPUs in the world in the cloud, especially those with encoders on. And even the ones that are being virtualized, you still need an awful lot of power. And that power costs money. And then they transfer that money onto the end user, or in this case, the business that's running it. So Adam Billiard came up with a new way of using command streaming instead of graphical streaming. So we use the power of the client to render the scenes, and we use commodity VMs in the cloud. What this means is we're not restricted to using AWS and Azure and Google Cloud and things like that. We can basically use any data center anywhere in the world, which has some very, very interesting challenges. So when I first spoke to Bruce, he said they'd already done their proof of concepts. They've shown that the streaming worked. They've got their angel investment. Everything was really great. Now they needed to prove that it could scale. And one of the USPs of the Polystream platform is that we can run from any data center. So just running something in Azure isn't really interesting to them. Running, a couple of VMs somewhere is not interesting. We need to show that it worked at scale. So these requirements of at scale and being secure and always up and everything else, these aren't abnormal things, right? Every platform aspires to have these things, but we needed these things from day one, which was interesting because I was the only service person in the whole company. I said the whole company, there was 5 of us at that point. So yeah, it was interesting. So I took my kind of Microsoft background and I kind of ran with Microsoft-based stuff. It was the easiest thing to use. So spun up some virtual machines in Azure to prove that we could do this stuff concurrently, and a couple of sort of full-blown cloud services. I don't know if anyone's used cloud services before, old-style cloud services, but they were essentially entire VMs running one service. So they took a long time to spin up. They were quite hard to manage, and when you wanted to kind of do updates and things, it just took time. It was, it's not the easiest thing. I had kind of history in managing these things, but it's not the easiest thing. So it wasn't very long before we kind of had these things up and running, and we could prove that we could run things concurrently, and everyone was very happy and looking for new investments and things like that. At that point, I could kind of take a step back. We employed another guy, so I wasn't on my own at that point. And I kind of set out a bunch of principles, things that we were going to kind of aspire to, I guess. The first is obviously cloud first. It's not really cloud first, it's cloud only. We don't really have anything that's not in the cloud. We are provider agnostic. We have to be provider agnostic. We can't be locked into any one vendor, because then that breaks our message of being able to stream from anywhere. I mean, one of the key things about streaming is it gets a really bad rep for things like latency, which although is not really an issue, it's perceived as an issue. So as soon as we can run our VMs in your data center down the road from where you live, it really helps. So if you're in Warsaw or something, the nearest data center of GPU is probably in Frankfurt, well, we can run it in Warsaw, and then that latency goes to nothing, which people really like. Lightweight deployments was really a kind of an aspirational goal, I guess, from being in that kind of cloud background with big heavy VMs. Deployments are a hard thing to do. You kind of have to notify everyone, and you've got to wait, and there's going to be downtime, and it was a real pain. So I really wanted to try and get to lightweight deployments. I didn't know how I was going to do it at this point, but that's where we wanted to get to. And telemetry and events, as the last talk, I mean, monitoring is hugely important, and we knew that this was going to be a globally distributed platform, and we're all in a little shed in Guildford. You know, we couldn't operate this thing without telemetry and analytics. So every single service we wrote had to have this in the fabric of it, that it really understood how to send this stuff out, how to tell us whether things were working or not. Didn't always work, but you know, that kind of, it was a goal. So then after we had some things running, and we kind of got together and we were talking about how we're going to move this thing forward. We started looking on the internet for how things are working nowadays. And containers had been something that's kind of been bubbling away over the years, and it was slowly gaining momentum. And we thought, sod it, let's give it a go. So we kind of read some blogs, and we just sort of thought, well, how hard can it be, really? So we spun up some stuff in Azure. We used Docker containers. There was a thing, I don't think it's even around anymore, Azure Container Service, which was essentially gave you the option of Docker Swarm, I think, DCOS or something like that. But, so we used Docker Swarm. It seemed like the obvious choice if we're using Docker containers. We did some proof of concepts, and it worked really well. And then we had to start spinning up these clusters on our own, because we couldn't rely on these managed services, because most data centers in the world don't have managed services for containers. You know, a lot of people hear about the bigger ones, even AliCloud and stuff like that. They have these managed services, but you know, Joe Blogg's data center down the road doesn't. So we needed to kind of bring containers to the data centers that didn't have containers. So we decided to do this. And then we started using containers in anger. We had containers everywhere, and it was brilliant. And then we came up with this idea that we're going to do container-first engineering. And the first thing is, well, that's, you know, container-first engineering is not really a thing. And you think, why isn't it a thing? Because everything's first nowadays. And the reason I don't think it's a thing is because you get test-first engineering, you get API first, and you get security first. The idea is that they apply restraints on things, and they restrain you so that you're ensured you kind of force down a path to make sure everything works the way you wanted it to work. The great thing about container-first engineering as a thing is that it removes a lot of that stuff. You don't have to worry anymore about the environment it's going to run in. You don't have to worry that, you know, we're going to run this thing in the cloud, therefore it has to work like this. You don't have to worry that when we come and we want to upgrade our .NET deployment, will the VMs be okay to do it? What's the path to update these things? So we decided that everything now, we're not going to worry so much about it. We're just going to include a Docker file in every service and let the engineer who's working on that service determine what the dependencies are and how that service is going to run in the environment. What it meant is that from a really, really early stage, kind of DevOps was really a thing for us. You know, the engineers were responsible for determining exactly how this service, I say the engineers, I was me and another guy, but we determined how these services were going to run. And obviously we knew that we was going to grow really fast, so we wanted to make sure that anything we wrote wasn't just throwaway stuff. It was stuff that we could keep going forward, and these are principles that we could apply as the team grew. So yeah, so we had many clusters around the world. I think maybe, I don't know, 6 or 7 swarm clusters scattered about the place. And we could kind of see this sort of mist on the horizon, and as it came closer, we realized that Kubernetes was around. And yeah, so you know, it was something. It kind of, for us, it sort of felt like it sort of jumped out on us a little bit. And when you sort of look into this thing a bit more, the community support was massive for this thing. Obviously, its background in Google was sort of, it was already a tried and tested platform. You really need to use this thing. Azure and AWS at the time were announcing Kubernetes-only services. So we started to sort of panic a little bit. It's like, oh my God, did we make the right choice when we chose Docker Swarm? So we sort of took the hit, and we decided as a kind of a gamble, I guess, but I guess a measured gamble, that that we'd move to Kubernetes. So I should have changed that slide earlier. There's also, yeah, loads of blogs. Loads of people were talking about their move to Kubernetes and how great it was and how wonderful it was. They didn't tell you how difficult it is to set up a Kubernetes cluster. It's not easy, especially because we're setting these things up in some random kind of unknown data center. You know, UpCloud, for example, in Helsinki. We run some stuff for Slush every year, and we run a region up there. So we just set up some machines, and you install Kubernetes on it, and you know, it's a challenge. So we now have Kubernetes clusters all over the world instead of Docker Swarm clusters, and we have thousands of containers running all the time doing various things, and we bring them up and tearing them down, everything's brilliant. And then what is, the inevitable question comes when Bruce, our CEO, comes up and says, by the way, I'm going to Bratislava next week. We need to make sure something's running there. Does it work? And we're like, probably, because no one really knows, because there's so much stuff. So it's not that we're sitting there thinking it doesn't work, but we're kind of a little bit oblivious to the fact that things might not be working. So what do? How do we know that these hundreds and hundreds of service instances that we're deploying are actually working? And the answer is obviously telemetry. But essentially, we come up with these things. So we actually came up with these quite recently. We're defining our kind of service level objectives and how we're going to determine whether things are up and things are working. So we thought to ourselves, we need to make sure, they ask us the question every time, how do we know it's working? Whenever we deploy any container, we want to know it is working. So how do you know that? Once you figure out it's not working, or it tells you in an ideal world that it's not working, how do you then find out what the problem is? Because again, something could break, in a message queue. Actually, the source of the problem is because someone sent a ridiculously large payload or something like that. And then the other one, which is the hardest problem to solve at all, really, is did it break when I wasn't around? Because then as soon as you look at it, you have this kind of weird kind of Schrodinger's cloud service issue where as soon as you look at it, it starts to work because the act of poking it brings it back to life. So these are all things that we decided we need to try and figure out. The first thing we did was heartbeats. So we use the health check services in Kubernetes and stuff like that, like everyone does. But we have a kind of a cloud agnostic operational model. So we need to make sure that our operational dashboards don't rely on certain things. So we needed this kind of single method, if you like, for monitoring the health of the services. So we had two types of services. We had the domain services that we wrote, which are obviously very easy. Just write some code and it will send some heartbeats. And then we had our third-party services. We had message queues and we had event streaming stuff and things like that. So we used this sidecar pattern of having another service that pokes it every now and again to say, how you doing? Got any stuff for me, kind of thing, and then send off some events. It turned out to be really, really, really efficient, actually, in doing this. So much so that we're actually in the process of moving all of our service heartbeats into this model, because it suddenly means that your domain service doesn't have to worry about sending heartbeats, worrying about having some other thread sit in there monitoring things. It just sits there and does its job, and something else is in charge of saying, are you okay? And it works really well. So now we have lots and lots and lots of telemetry. We've already said that telemetry is absolutely first class. It sits at the kind of the bottom layer of every service. We send telemetry, we send a lot of telemetry. We also had this requirement from the network team, that network team being one guy, that we wanted per frame technology. We wanted to know how long the compression took for one frame in any one stream on the server, for example. So we started sending events every frame from the client and server. So this is, say on a 30 FPS game you're playing, obviously that's 30 events you're sending per second from the client and 30 events you're sending from the server. That's 60 events a second from every stream. We have to process that, ideally in real time. It's obviously not in real time, but as close to real time as you can, and obviously maintain it. And it's not an easy thing. So like most people, I think we decided it was kind of a build versus buy kind of thing when it comes to our telemetry pipelines. We did look at other things. We looked at Logstash. We were using Elasticsearch at the time for putting our devlogs in. We looked at Logstash. It wasn't really performant enough for what we needed to do. So we decided to roll our own. Why not? I mean, again, how hard can it be, right? There's two of us and we got in a massive distributed platform. Why not spend some time writing our own service? I don't know. With hindsight, you think maybe not, but it seems to work, so it's cool. So we wrote this thing called Teleminium, which is it's very similar to Logstash kind of in concept. It's a customizable pipeline. It has its own kind of expressive syntax to describe these pipelines. It's entirely cloud native, obviously. And it's a plug-inable architecture. So we have one service and you can plug in an HTTP listener to it and send it through, do some modifications. Unlike Logstash, you don't have to create plugins for manipulating the event as it goes through. It can all be done in real time. So what this allowed us to do is, like I said in the previous talk, when you want to trace messages and events from a service somewhere, we don't really want to put too much information. We don't want to configure a service to say you are running in Warsaw. We just want it to be a service that's just sitting there doing its job. So as it sends its event, everything goes through these telemetry instances, and each one has more awareness of where it is. So it tags the events on the way through. So what we end up having are these kind of standalone single responsibility services, but by the time the telemetry gets to the other end, it's completely enriched with all this stuff. We've had spillage on the floor. That's all right. It's not your office. It's cool. Yeah. So the other thing we do obviously is trying to collate this information in order to get some kind of holistic view of the platform, because there's a lot of providers, a lot of services and everything else. We use event sourcing for our kind of operational dashboard stuff, so it kind of collates, it listens to Kafka and collates all these events and builds up its own little snapshot of what the service state looks like across everything. And everything worked really well, and it's kind of going good, and everything's great. We had these teleminions, we started using them everywhere. We ended up with about 40-something different configurations of teleminion around the world. Essentially every component that spoke to another component went via a teleminion for some reason. The problem with that is that you end up with ridiculous amounts of configuration. So we had, our CI builds were pumping out we check in a teleminion instance, and it had to go and recreate 40 or 50 container images, each one with separate configuration, because we didn't know what else to do. I mean, up until this point, we were deploying using PowerShell and ARM templates and stuff. We also found that because we were doing everything with ARM templates, we started to slip a little bit on our cloud agnostic stuff. You know, it was easier to use ARM templates we already had than go and try and figure out how we provision something new in Cloud Sigma. You know, so it was hurting us a little bit that we weren't managing this configuration properly. So we turned to Terraform, as everyone does nowadays, right? Everyone uses Terraform. It's a great thing. You know, we used it. It's a lot of community stuff. It's a tried and tested configuration management system. It's kind of plug and go, although we've had to make modifications to almost every module we use. You know, and it is easy to integrate. I mean, it's a good thing. It takes a little while to kind of get it working and, you know, really figure out how to use it properly. And we're kind of on our second iteration of how we manage these configs. But we're sort of in a good place of it now. Yeah, and it seemed a good idea at the time. I mean, it's slightly more tricky when you go true cloud agnostic, and Terraform isn't really that. You know, you still require TF files for every single provider you want to integrate with. But anyway, so now we're in an even better place. We have a configuration. We've got all of our config in GitHub, and we have our configuration builds, and we've got everything, and we're in such a great place. We think, let's use more containers, because containers are solving everything for us. So what we ended up doing is we started to think of different places we could use containers that were going to help us grow. Because again, at this point, there's probably 3 of us, maybe 4, I can't remember. Yeah, so, you know, containers are helping us big time. So we said, well, where else can we use containers? So we have quality of service servers that we run around the world. So when we determine where the best stream is going to be for you, so, you know, you're in Warsaw, for example, you want to ping a few servers and say, well, actually, even though Warsaw might be physically the closest data center, just because of who my ISP is and peering agreements and everything, it's actually quicker to go to Czech Republic or something. So we have these ping servers, and they're essentially just standalone Linux VMs that just run a service, and, you know, everything's really great. But actually, we still had the same issue. We want to upgrade .NET. Well, we update .NET Core. We now have to go and update all these machines, and then we've got to run them side by side to make sure things roll over properly. So we decided, well, let's just pack them up in another container. So now we have a machine that just runs a Docker engine that we just throw a container on. And it works brilliantly, because our upgrade path is so simple. And then obviously we want to roll back because things don't work. Again, it's really simple. You haven't got to worry about any state that you might have. You haven't tainted the machine in any way. You just throw a different container on there. Our CI builds, as I sort of said previously, that every service builds its own container. So you check in some code for a service, or, you know, our kind of underlying infrastructure stuff. The service is the code's in GitHub. It gets built by Azure DevOps, is it called now? The TFS, TFO, online VSTS, I don't know, whatever. It runs through the pipeline and does the builds and does tests and all that kind of stuff, goodness, and then ends up by building this Docker image that pushed into our repo. We also, now that our configuration is in source code, we have builds for our configuration. So as soon as you check in a new configuration, it might be maybe a service version update or something like that, that kicks off a CI build, which in turn takes all that information. It builds. We take the Terraform files And then we build a container that contains everything you need to run Terraform. So essentially, the command line, the execution way is Terraform, apply my stuff. You know, and again, it works really well because this allows us to get to that point where deployments are lightweight. But all we do now is we can take those containers, because they're in our Azure CR container repository, from any machine that has a Docker engine on it, we can deploy code, we can deploy services. But more than this, it means that with our deployments as containers, we can now deploy these things at runtime. So we can spin up new regions without engineers getting involved. You know, from our operational dashboard, we can say we want a new bunch of agents running in, I don't know, San Jose or something. You click a button and it creates a Kubernetes job that just runs these containers to go and create new services. And because we have all our heartbeat stuff in every service, and every service is responsible for telling us how it's doing, as soon as that comes up, we know that the service is there and it's instantly monitorable. We also don't have any kind of service discovery, apart from what's obviously inside Kubernetes. We don't have our own service discovery. Everything is dynamic. So the existence of a path to a service means that that service is there. And we use teleminions in the middle. So we used to use RabbitMQ shovels, as I've used them before. It's really good. It does the job. It takes messages from one RabbitMQ and shoves it in another RabbitMQ. But it's not very open about how it does things. And the events you get out of it aren't great. It kind of says, I couldn't do it, and that's what you get, really. So we use a teleminion in the middle that has a RabbitMQ input and a RabbitMQ output, and we can actually manage the bits in between and say, well, I couldn't route it because there is nothing listening to the queue, or because the queue's broken, or whatever. Or something that happened recently, our RabbitMQ cluster split in two, which was really odd. Never seen that done before. And also, so the final thing that containers kind of give us really is that we can just throw stuff up there and just try things out. With Kubernetes, obviously, we just go and create a YAML file, and all of a sudden we've got something tested. So this is really useful for, again, we're being a very, very, very small team, and obviously most of these operational challenges we face are because we're so small. But because we're small, we want to go and try out something with Splunk or something, right? We use an Elasticsearch, we're throwing our metrics into Datadog, it all works really well, but actually what if we used a slightly better managed service so we don't have to worry about Elasticsearch anymore? Well, we can now just create a teleminion, we write a bit of config, we throw it up as a service. Because it's listening to Kafka, it grabs all the services from the beginning of time, however long we've set that retention period to, and instantly you've got all that data in there. And you now have a standalone service that is being monitored, it's part of the platform, but actually you haven't really had to do anything to get it up there. And there's no real operational overhead. So that kind of brings us on to where we are. This is really bad diagrams now, so I apologise. So our topology for the platform is hierarchical. We have obviously our global kind of infrastructure-y kind of operational bits. They go out to centrals, which is kind of the point of presence for the platform. It's where clients call off to determine where they're going to get their stream from. And then that gets farmed out to regions, and then beyond regions you have your actual streaming agents. So it's very much a hierarchical thing. And if you look on the right-hand side, that kind of diagonal down there, there is a kind of slice of what our architecture looks like. Again, I apologise. So from kind of right to left, this is sort of a global central region, and then at the very end is a streaming agent. And each of these, so this section here is a Kubernetes cluster, this is a Kubernetes cluster, and that's a Kubernetes cluster over there. And how are we doing time? All right. So we use RabbitMQ. So we have RabbitMQ in each of the clusters. That's obviously how we do our discovery. We use AMQP. It works really well. And our messages flow from right to left with kind of a request response kind of thing. And then we use Kafka for our event streaming, getting all our metrics back up. Because again, this stuff's running in lots and lots of different data centers across the world. We can't hold things up when we're sending these telemetry events back. And ultimately, everything needs to be aggregated so we get this kind of holistic view without going to lots of different dashboards and things. So we use Kafka for that. And all the events, as they get sent back, they get tagged, and ultimately stuff gets back. We do kind of siphon things off from time to time to different places. But a lot of our telemetry ends up back in our kind of global, that we call. We have a lot of teleminions running. I put a question mark because we don't have an icon for it yet. If anyone wants to create a little logo for teleminion, you're more than welcome. We have lots and lots and lots of teleminions. It probably makes up about 80% of our platform is this one service. It's so easy to configure and it's so easy to deploy. You can kind of just knock something up on your machine, test it, throw it up there and just see what happens. It's really useful. So I guess to summarise really, we have this dynamic topology that we don't have any kind of central registries of services. We haven't got a single point of failure. If that goes down, then all of a sudden you can't find anything. We use containers and more specifically deployments of containers at runtime. Lots and lots of telemetry, and everything is monitored via our operational dashboard. I should have put a slide about a dashboard. It just doesn't look very nice. It's just tables and tables and tables of stuff, and there's a hell of a lot more. So the future, no one really knows what the future looks like, right? We work in a startup. It changes all the time. The business vision will change from, well, maybe not daily now, but it changes quite often. But we need to try and stay kind of ahead of the curve, really, and containers and Kubernetes specifically. I appreciate there's a Docker meetup. It works, and it kind of puts us in a good place. So we'd like to get to the point where we can have automated deployments. Obviously, everyone loves automated deployments. They're a bit of a unicorn. Never really worked anywhere that's done it properly. Everyone says, yeah, we can automate deployments. But really and truly, there's still a guy sitting there pressing the button, watching the log. Intelligent scaling is interesting for us. We still use full-blown VMs for the streaming. We need a Windows operating system for that. Windows containers are just too slow at the moment. So we'd love to get to the point where we can, scale on demand, but it's a hard thing. We don't know how we're going to solve that yet. Containerized streaming agents, we would like to get to that. We think that will help with the intelligent scaling. We have some proof of concepts running streams from Windows containers, which is a brilliant thing. If you think at the moment, game streams run from massive VMs in the cloud with huge NVIDIA grid GPUs attached to them, and we can run it from a container. I mean, it's massive. The scale is just beyond anything that's available at the moment. Larger scale, I mean, most of the people that we talk to, the people we work with, the publishers that we work with and the game companies, they always want, as soon as they hear what we do, they want to do it big. No one ever wants to say, yeah, go on, run 5 streams and see how it goes. It's, yeah, we want thousands of streams. We've got this massive event over the weekend. We want you to stream all these, millions of things. So it's going to get, very, very, very big. If anyone fancies trying it out, you're welcome to. We have a demo on demo.poly.stream. Don't do it from a mobile, it doesn't work. And don't do it from a Mac, because it doesn't work. You have to do it from a PC, like a proper computer. Sorry. Yeah, exactly, that's fine. Yeah, so, and give it a go, it works. It'll do a little speed test and make sure you're within range of a decent data center. And because I'm giving a talk at a meetup, we are obviously hiring, because you're not allowed to give a talk unless you have a we're hiring slide.
You are.
Who said that?
You are allowed to do that without having a slide like this, but it's fine.
I think we have to. We're hiring across the entire business. I mean, I'm obviously very interested in the platform, but across the business. And any questions?
Mine's not a question, it's a comment.
Oh, go on then.
You realise your proper computer comes with Candy Crush installed on it, right?
What's wrong with Candy Crush?
Anyway,
Just saying.
Yeah,
do we have any questions?
Oh, I thought I was going to say awesome.
Does this work? Yeah. Excellent. You mentioned Windows containers being too slow. Do you mean too slow to start?
Yeah, too slow to start up. I mean, from a runtime point of view, it's just Windows, right? It's fine. And we run on Windows now. There's business reasons why we run on Windows. There's business reasons why we stream to PCs opposed to anything else. But yeah, it's the startup time. I mean, we've been playing with server core. It's a couple of minutes, really, before it's really up and
Have you
running,
done anything with 2019?
Not yet, actually.
2019 is much better.
There's some interesting licensing issues.
oh, yeah, always.
Yeah.
But the technology is better.
Yeah, that's all right. We'll just stream from Linux containers. It'll be fine.
Cool. All right. Next question.
Very quick one, just about Docker containers on Windows. I assume if you're just doing a bit of local dev, you might run into the issue of Windows containers running into a memory limit. So at the moment, essentially, if you want to run Windows and Linux containers side by side, if you've got some sort of stack.
No, well, actually, we don't run Windows containers.
Okay.
Generally speaking, I mean, the infrastructure builds we create are Windows containers, but the actual we don't really run any containers with Windows. So all of our quality of service stuff, the stuff that we just run as a container on a single engine, that's always Linux of some flavor, various flavors. All of our services run in Linux. We use .NET Core for that reason. We develop on Windows machines, but we run it there. If we're testing anything locally, we tend to just run it in Linux containers.
Very cool.
Yeah.
Thank you.
Sorry.
Cool. Anyone on this side of the room, maybe? I mean, the questions have been coming from this side so far. No? I mean, give a round of applause.
Thank you.